Hi, we're starting Unit 2 now. This is fairly different from the rest of the course, although it has some similarities. And I guess this video has a lot of new information, so you may want to take notes or watch it a couple of times. So what we're going to be studying is infinite sequences of numbers and also infinite sums, which are called series. Um, so you should probably ask yourself why. Well, these are going to give us powerful tools to do many things like approximating numbers. For example, how does your calculator know what e is or pi? Um, Approximating functions, definite integrals, even when we can't find their antiderivatives, and more. So it's a very powerful tool that has a little bit of a different flavor than most of what we've done, but it's also, it is what it is. So let's see. Sequences are just infinite lists of real numbers. So here's a few examples. And usually the sequences we're interested in studying have their terms described by a simple pattern or formula. And we typically say A sub n or B sub n is the nth term of the sequence. So sometimes we have to be specific about where we're starting. Um, but then this formula, right, tells me, has all the information of the sequence itself, right? Tells me each term, term by term. For the Fibonacci numbers, there you have to go back and add up the two previous terms to get the next one. So for that one, you need two initial pieces of data. So that one's a little bit more complicated, but it's an example people have heard of sometimes. So, ooh, screen went blank for a second there. Okay, hopefully we can see that. Um, so here's a couple other examples that don't have special names. It's just I can define whatever I want, and that's what you get for those two examples. Okay, so it's being a little bit slow. Here we go. A sequence converges to a number L at if, as we go farther and farther out, the numbers of the sequence get arbitrarily close to L. And then we call that the limit of the sequence. So, for example, this sequence is apparently approaching the number pi. Here's a few more. Sequence approaching 1, 1/3, and the sequence 1 over n approaches 0 as n approaches infinity. So here is the notation for that. It's just limit of a sub n as n goes to infinity, and L there is whatever the limit of the sequence is. Um, so that's just an example of the notation. Probably no surprises there. Another thing that isn't very surprising, but sometimes seems to come out of nowhere is given a sequence, we can often just replace the n with an x. And the meaning of that is just thinking of it as a function defined for um, an interval of real numbers rather than just like positive integers or something like that. So when the corresponding limit of the function exists, so limit of 1 over x as x goes to infinity is 0, that will be the same as the limit of the sequence. Okay, so here's our first example. here's a sequence defined by this ratio of quadratic expressions um, in the index n, and it just says find the limit of the sequence. So I need to evaluate this limit. And you could change this into x's and use L'Hopital's rule. I'm actually going to do it a different way. I'm going to take the highest power of n that occurs in the denominator, which is n squared, and I'm going to divide by that in the numerator and the denominator. And sort of distribute that through on top and on bottom, and I got 2 minus 3 over n plus 1 over n squared divided by 5 plus 4 over n minus 7 over n squared. And then since n is approaching infinity, each of these terms is approaching 0. So this limit is 2/5. Okay. So far, so good. So what does it mean for a series to converge? Well, an infinite sum of numbers is called a series, and that may seem like a strange thing to be thinking about at first. We actually think about it quite often. So for example, any number with an infinite decimal expansion, like a 1/3, can be thought of as a sum of all of its decimals. Um, So 1/3 is a pretty reasonable number. Um, or take a number like pi or e. Those also have infinite decimal expansions. Um, and so it's actually not that weird if you believe decimal expansions. Notice though that these numbers are getting smaller very rapidly, and that's a theme that's gonna come back. So when a series doesn't converge, it's said to diverge. And we'll define this in a moment, but basically it's analogous to limits of functions that it can either diverge to infinity or it can diverge by oscillating. So here's two examples of that. The top series 1 plus 1 plus 1 plus 1 forever, it's going to diverge to infinity pretty obviously. And then the bottom one, 1 minus 1 plus 1 minus 1 plus 1 minus 1, it's certainly going to be oscillating. And we'll make more sense of that um, after we define rigorously what it means to converge and diverge. But there certainly seems to be a different thing going on with those two examples. And that's all I want you to think at this point. So notation for a series. We're adding up infinitely many numbers, so we need some efficient way to write that down. Here we go. So we're going to use sigma notation. So before we talk about infinite, here's just a finite sum. And this n here is called the index. That's a counter that starts somewhere and goes up by 1 every time. So this expression here is equivalent to this one. The counter starts at 1 and it goes up by 1 until we get to m, whatever that is. So here's an example. The sum from 3 to 7 of 1 over n squared. Okay, so a series then is just a sum from, it could be from 1 to infinity or 12 to infinity or negative a million to infinity. It doesn't have to start at 1. I just did that to simplify the notation a bit on this slide. But it certainly should go on forever. And the question is how to make rigorous sense of that. So what we do is associated to any infinite series like this, we can form its sequence of partial sums. So what that is a sequence we build out of this infinite sum, where the first term is just the first term that we're adding up. The second term is the sum of the first two terms. The third term is the sum of the first three terms, and so on. So the kth term is the sum of the first k terms of the series. So this is a sequence that tacks on one more term every time. So here's the definition of series convergence. Although we can't manually add up infinitely many numbers, we can examine the sequence of partial sums and see if it converges to some limiting value. So this is the definition of convergence. Given a series S, we say that S converges to a value L if the limit of the sequence of partial sums is equal to L. If this limit does not exist, then S diverges. And specifically, if the limit is plus or minus infinity, we can be specific and say S diverges to plus or minus infinity. And that just we're just giving as much information as we can, just like with limits. So the first kind of series that you study is geometric series. They're the simplest kind. And what makes a series geometric is that from one term to the next, we multiply by a fixed constant, which is generally called R. So here's an example. 3 times 1/10 to the n from 1 to infinity. So the first term there, when n equals 1, is 3/10. When n equals 2, that's going to be 3/100ths, and so on. And these are the same decimals we added up earlier to get 1/3. So we know, because we trust decimal expansions, that this infinite series converges to 1/3. So it turns out geometric series have a simple formula that tells us the answer. Does it converge or not? And if it converges, what number does it converge to? And especially that last part, we don't typically have a nice formula for that for most series. So it's pretty nice that if we remember this formula, we just know the answer. I will point out it's important that n is starting at 0 here. So if it started at like 5 or something, then you'd have to, this wouldn't be quite right. You'd have to adjust it a bit. So this formula, it's important that we're starting at 0. So let's actually see how that plays out with that example, because the example here n starts at 1. So this is a good example because we know the answer. So let's see how to work with the geometric series and reason that out. All right, so what that formula tells me is the sum of this series. So here our R is 1/10, which is less than 1. So we know that the series converges. And then what that formula tells me is that this will equal A over 1 minus R. So that's 3 over 1 minus 1/10, which is 3 over 9/10, which is 10 over 3. Now, that is not the answer to the original question that was asked. right? Because the original question was having that index start at 1. This starts at 0. So this is equal to the sum starting from 1, which is what we're actually trying to solve for, plus the n equals 0 term, the a0 term. So the a0 term is just 3, because it's 3 times 1/10 to the 0. So that means our answer that we really want is the total sum starting from 0 minus 3. And 3 is 9/3, so we get the 1/3 answer we were hoping for. Strategy 2 is to take the series the way it was written originally and re-index it. So what that means is change your counter. So here this m is equal to the original n minus 1. And then I have to think a little bit about what the first term should be. I know the first term of that series, we had written 1/3 as like 0.3 plus 0.03, right? So that first term should be 3/10. And you can check when m equals 0, we get 3/10. So this is adding up the right stuff. And now that it's in that form, I just apply the formula a over 1 minus r. So that's now my a has changed. My a is 3/10. My r is still 1/10. Hey, get out of there. So that's 3/10 divided by 9/10, which is also 1/3. So either strategy will work, and it's just a matter of preference, how you like to do it. All right, so here's a try it yourself, or two, I guess. First, take each of these series and write them in sigma notation. Then determine whether they converge or diverge, and if they converge, what do they converge to? So maybe pause the video and figure that out. And 3, 2, 1, here's the answer to number 1. This diverges because the ratio r is greater than or equal to 1. And number 2 converges because the ratio is 1/5, which is smaller than 1. All right, so that's it. Nice going, and see you next time.